Good day. Thank you for coming and looking at this video with me. The title is Linear Programming, and it does serve as a little bit of an introduction to mathematical modeling, and it lines up very directly with Chapter 5.6 in your textbook, although I'm going to be doing some examples that are not the examples in your book. So I'm going to begin just with a little bit of a story, math history story. The fellow that you see on the left is a guy by the name of George Dantzig, and it turns out that George Dantzig was the father of what we're talking about, linear programming, and he was a great mathematician, and one of the reasons I'm very fond of talking about him is I actually studied with one of his students, and so I'm sort of a grandchild of his in that respect. There's an interesting story, and he actually was quite a character. His student told me many things about him, and so I'm going to read this thing that's on the left-hand side here. During his first year at Berkeley, he arrived late to class one time, and there were two problems on the board that he copied down. A few days later, he went to his instructor and apologized for taking so long to do the homework. The problems seemed to be a little harder than usual, so he asked if he still wanted the work, and he told me to throw it on his desk. I did so reluctantly because his desk was covered with a heap of papers, and I feared my homework would be lost forever. 6 weeks later, one Sunday morning about 8 o'clock, Ann and I, that was his wife, were awakened by someone banging on our front door. It was Neiman. He rushed in with a paper in hand, excited. "I've just written an introduction to one of your papers. Read it so you can send it away for publication." For a minute, I had no idea what he was talking about. To make a long story short, the problems on the board, which I had solved, thinking they were homework problems, were in fact two famous unsolved problems in statistics. That was the first inkling I had that there was anything special about them. Linear programming, which is one of the things he developed, is viewed as a revolutionary development, giving man the ability to state general objectives and to find, by means of a simplex method, optimal policy decisions for a broad class of practical problems of great complexity. And in a real world, planning tends to be ad hoc rather than quantitative because many special interest groups have multiple objectives, but this gives them a way to deal with the problem. Now, in order to do linear programming, you have to be able to graph inequalities in two variables. Now, this is a prerequisite that you already have, and you've studied it before. This is something taken from your book, but I will talk about it very briefly. One thing is that you can sometimes graph it by solving for y, and then you'll talk about either all points that are above or below the line y equals f of x. Another way to do it is to use a test point, and I'm going to illustrate both of these, and I know you've studied all this before. So let's begin then with an example just of this technique. So the example that we're going to talk about is this one, and so what we want to do here is we want to graph 3x minus 2y is less than or equal to 6. So we're talking about all points in a plane such that that is true. And so here is your approach. First thing is you consider the boundary, and you say, okay, I will look at the boundary, and that is where 3x minus 2y is equal to 6. And since I have less than or equal to, I'm going to include the boundary, and so the line I graph will be solid. So I'm looking at that line. 3x minus 2y is less than or equal to 6, and I just pick some points. So if I pick x to be 0, I will get y is minus 3, and if I pick x to be or y to be 0, I would get x is 2. So I plot those 2 points over here, and what I have is a line between the 2 points. So that is the line. The line is included because I have equal here, and so now all I have to do is use a test point called 0, 0 to see if that works. If 0, 0 works in that inequality, that means that the half plane containing 0, 0 is there. If 0, 0 doesn't work, that means the half plane, it's the other half plane. So let's talk about that. If I let x to be 0 and y to be 0, I get 0 minus 0 is 0, and the question is 0 less than or equal to 6? And the answer is yes. So that means the half plane that I get is all of these values up here that are in the half plane containing 0, 0, because that is where 0, 0 is. So that is an example of doing graphing one of these things, and that is in fact using the test point approach. Now we'll look at a second example, and this next example is different. Instead of being less than or equal to, it's going to be strictly greater than. But the approach is going to be pretty much similar. So we start with x plus 4y is greater than 4. But then what I'm going to do is I will consider the case where x plus 4y is equal to 4. But since equality is not allowed, it must be greater than, the line is going to be dotted. And I hope you can see here that the line this time is dotted rather than being a solid line. And I'm going to do a different thing. I could just pick points and do the test point thing, but this time what I'm going to do is I'm going to solve for y. So I work through and I solve for y following this path, and then I say that y is bigger than minus 1/4 x plus 1. Now what that means is that the y values are bigger than the line, the dotted, so that means that it's everything up here that is the half plane, and so those are the points that satisfy that inequality. Now what we're going to do is begin talking about linear programming. And again, except for the marginal notes, these things are in your book, but we'll talk about the fundamental theorem of linear programming, which is kind of an interesting theorem. It says that the optimal value, that means the best value, the solution, if it exists, it occurs at a vertex of the region of feasible solutions. So what that means is all you have to do is find the region of feasible solutions, find the corner points, and just check the corner points. And that's going to be the optimal solution, either a maximum or a minimum. And here's the process that you go through. Usually you're starting with a word problem because life is a word problem. But then you say, what is the objective function? And you write that down. Now the objective function will either be a max or a min. And then you talk about what constraints are involved in the problem. You get this from a reading of the problem. Now, a feasible region is a place in the plane where all the constraints are simultaneously satisfied. That means it's the intersection of all the constraints. So you have to graph the feasible region, and that's step 2. Step 3 says you have to find out all vertices or corner points. Now that requires you to solve simultaneous linear equations and figure out where do these all intersect. But then you can use the fundamental theorem of linear programming to say, oh, but my maximum or minimum must happen at one of those vertex points, so I just test each one of those into the equation and see what is the max or the min. Now there really are two answers. It's what's the best you can do, what is the maximum or minimum, but the second question is, and how do I achieve the maximum or a minimum? A lot of times I will talk about a consultant coming to the College of DuPage and telling the president of the college that he can save $1 million. Then the College of DuPage president would say, well, okay, that's great, I like $1 million, and tell me how to do that. Well, the x and the y values are how do you do that, and you will achieve the optimum value of that. Now, we're going to do relatively simple problems, but it turns out that what Danzig invented worked for much, much larger problems. And in fact, probably the largest use of computer time for solving mathematical problems is spent doing mathematical programming and, in fact, linear programming. So let's then begin and talk about an example where we are applying these techniques. So here we go with this problem. I will read it with you. And I think you can see that, oh, this is a good problem. I mean, it makes sense. You would want to solve this. An agency wants to ship food and clothing to tsunami victims in Japan. They have planes that will transport these packages, but they have to fit in available cargo space. For each 20-foot cubic box of food, it weighs 40 pounds, and each 30 cubic foot box of clothing weighs 10 pounds. And they have a weight constraint. They can only put, the weight constraint is the total weight cannot exceed 16,000 pounds. And the total volume cannot exceed, as it says here, must be at most 18,000 cubic feet. You see, they have to fit it in, and the plane still has to be able to fly. Each carton of food will feed 10 people, and each carton of clothing will help 8 people. So each carton of clothing will help 8 people. So the questions that are posed here now in real life, you invent the question and you have to come up with this. But what they're saying is, how many cartons of food and clothing should be sent to maximize the number of people assisted, which is what you would like to do with sending this aid. And then the answer, so that's kind of saying, okay, so how many cartons of food and how many cartons of clothing should you send to do that? And then the second thing is, and gee, how many people can we help with this aid? So we're going to go through all of those steps that we just talked about in terms of defining an objective function, defining our variables first, defining an objective function, writing what the constraints are, graphing the feasible region, finding the corner points, and after that we're going to substitute values in and see what's the best we can do. So let's begin. So first of all, we're going to define the variables. And the variables are, we're going to say let x be the number of boxes of food and let y be the number of boxes of clothing. So we've defined some variables. Now we're saying, what are we trying to do? Well, for each box of food you can help, it says 10 people, and for each clothing you can help 8 people. So what we're going to say is, we want to, this is called the objective function, I want to maximize 10x plus 8y, because that counts how many people based on the problem. And ST means such that, because now we're going to talk about the constraints. So one of the constraints that we have is that a box of food is in volume 20 cubic feet and weighs 40 pounds, and the clothing is 30 cubic feet and weighs 10 pounds. So we have to satisfy both the volume constraint of not exceeding 18,000 rather cubic feet and not exceeding 16,000 pounds. So that means that, using the variables that we have for volume, that 20 times x plus 30 times y must be less than or equal to 18,000, because this is the maximum volume, and that's how much volume is in each of those boxes. And we have a weight constraint as well, and the weight constraint says that 40x plus 10y has to be less than or equal to 16,000. Now there is a technical issue, because we can't end up with negative values, so x must be greater than 0 and y must be greater than 0. So please realize we're going to be graphing 4 constraints. One of them is here, one of them is here, and 2 of them are here. So we're going to be graphing all of those, and we'll look at the places where they all overlap. So I'm going to be doing the things that we did before for these 4 inequalities. Okay, so let's move on, and I will do that. So now here what I did is I have graphed the lines where these things are equal. And what happens is that I wanted x to be greater than 0. That means you start there, that is where x is equal to 0, and it's going to be that half plane. We also say that y is greater than 0, and so it's going to be the half plane above that. This constraint we said was less than or equal to y, and this one was also less than or equal to. So that means that this part in here is my feasible region. Now what I'm going to do is I will take each of those lines and see where they intersect. So I will get one point here, which if you take the line, let's see, that is going to be x equal to 0, and this equation here that I graphed, those will intersect at this point. So that's a corner point. I'll similarly get a corner point here. One corner point is going to be 0, 0. And the last corner point is going to be that one. So you see, I found my feasible region. This is the feasible region. It was where all those constraints intersected. And now I found the corner points by solving simultaneous equations. And now I have corner points. And so what I'm going to do is I'm going to check each of these corner points into the objective function. And you want to remember that your objective function was this one, 10x plus 8y. So I'm going to be taking those values of x and y, plugging it into my objective function. So I'm going to do 0, 0, 0, 600, 400, 0, and 300, 400, and see what happens. And what happens when I substitute that in, I get these numbers. And so my objective function is 0, 4,800, 4,000, and 6,200. Now I wanted to maximize the objective function, so this becomes my answer. So we can help a maximum of 6,200 people by sending, and X was, I need to remind myself what X was. X was food. By sending 300 food and 400 300 boxes of food and 400 boxes of clothes. So you see, we solved the problem by going through the steps that we spoke about. Let's solve a second problem, and it's going to be this one. I will read it to start with, and then we'll go from there. Theo, who is dieting, requires 2 food supplements, 1 and 2. And you could think about those as being vitamin C and vitamin D or something like that. He can get these supplements from 2 different products. You could think about these as multivitamins, A and B, as shown in the table. So the table shows you that product A gives you 3 of supplement 1 and 2 of supplement 2, and product B gives you 2 of supplement 1 and 4 of supplement 2. So his doctor has recommended they include at least 15 grams of each supplement in his daily diet. So so that means you have to be, supplement 1 must add up to being more than 15 or more, and supplement 2 he wants to also be more 15 or more. And product A costs 25 cents per serving, and product B is more expensive. It is 40 cents per serving. So how can he satisfy his requirements most economically? And that means at minimum cost. So now what we have to do is define our variables, define our objective function, define our constraints, and then we'll work to solve the problem. So here we go with a solution. First of all, we're going to let X be the numbers of servings of A that will be required, and Y will be the number of servings of B. And our goal is to minimize the cost, so the cost is going to be 0.25 times X plus 0.40 times Y. And then we have some constraints, and the constraints are these. What must happen is if you add up 3 times X plus 2 times Y, and you can see those are the values that he is getting of supplement 1. This is the constraint dealing with supplement 1. It must be greater than or equal to 15. Similarly, 2x plus 4y must be greater than or equal to 15 as well. 2 times x plus 4 times y is how much of supplement 2 he gets. And then again, we have to have non-negativity constraints, because we can't be getting negative numbers of servings of these things. So x must be bigger than or equal to 0, or y must be bigger than or equal to 0. Again, what we're going to get is 1, 2, 3, and 4 constraints that we have to be graphing. Then we're going to find where these things intersect. We're going to find the feasible region. And then we're going to find out where these things intersect, and then we'll look at the corner points of the feasible region, plug them in, and we'll evaluate them relative to the objective function, and we'll find out what's the cheapest that can happen, and how much of x and how much of y does Theo need in order to satisfy this problem. Okay, let's graph them then. So here is the graph that we come up with. Now, x being greater than or equal to 0 means we have to be on this side of the y-axis. And y being greater than or equal to 0 means we have to be on this side of the y-axis. But then what happens is you have to be bigger than or equal to 15, so it's going to be up here when you check the inequalities. And it's also going to be up here when you check the inequalities. So you look at where all those things are satisfied, and what happens is this is your feasible region is up here. Okay, it stops at the y-axis, and that's what we get are those places. Now, if we start looking at corner points, then this is a corner point because that's a corner point of the feasible region. This is not really a corner point of the feasible region because you have to be bigger than this one, but also bigger than that one, so we're up here. This is a corner point of that feasible region, though, as is this. And you see, this is the feasible region. There's a boundary there, there's a boundary there, and there's a boundary down here. And you can see that this feasible region actually is unbounded. It goes up there, but I have a number of corner points that I have to evaluate. I have 3. I have this one, I have this one, and I have this one, and the coordinates of this one are given here is 15 over 4 and 15 over 8. Now you do have to go through and solve those linear equations, but that's what we've studied in the rest of chapter 5. We know how to do that. So what we then do is we go back to the objective function, and remember that the objective function was this one, 0.25 times x plus 0.40 times y, and we see which one of those corner points does better for us. Now, those corner points were 15 over 8 and things, and what happens is when I was doing the calculations, like this would be 15 over 2, that's 15 over 2, so on and so forth. I actually used fractions, but these are the values that I get. Now remember what we're trying to do on this problem. We're trying to minimize the value of the objective function. And we go back and we say, yeah, we're trying to minimize that. So what we want to do is we want to find the minimum value of the objective function, and the lowest one of these numbers is here. And that's about $1.69. So it's going to cost him about $1.69, and what he should do is take 3 3/4 units of that, okay, and then he should take, let's see, that is 875, so, and that's going to be, let's see, that is 15 over 8, or 1 7/8 servings of vitamin B. So you see, again, we found that the optimal value is the minimum cost possible is $1.69 and achieved by 3 3/4 servings of A, and let's see, that would be 1 7/8 servings of B. So that's the solution of this problem. And so we've done a maximum problem and a minimum problem, and you do have one of these that you're supposed to do as part of a take-home contribution to your final, so bring that to the final. Thanks for watching, and oh, I guess I now have this. So now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. Take care. Bye.